each type of number based off of its subsets. So if we're talking about classifying number 2, then I need to be able to identify the best description for that, and also be able to apply or identify what all types of numbers classify. For the second one, we need to be able to order real numbers from least to greatest, greatest to least, or also just compare real numbers. They're all going to be written in different forms, but we need to be able to use our properties to understand real numbers. Looking at the first slide here, I know that natural numbers are the counting numbers. This basically means that I am going to use my fingers. In elementary school, that was the way that most students counted. Any number that I can use my fingers with are considered counting numbers. The second one will be whole numbers are the natural numbers. So that basically means that any number that was a counting number, such as 1, 2, 3, 4, and so on, are also going to be considered our whole numbers. We also have 0. 0 is also considered a whole number. I can have a whole pizza and have eaten it, and now there is 0 left. 0 slices left. That's considered a whole number. For our integers, we know that we talk about our number line. I always like to use my number line as a resource or description of what an integer is. So when we talk about an integer, at least we are talking about our whole numbers plus the negatives. So if we look at this, we have 0, 1, 2, 3, 4, and so on. And we also have the negative values. So -1, -2, -3, to negative infinity. So those are usually my descriptors for when I'm labeling a number line. For the rational numbers, we know we are talking about all of the above. It can be a whole number, it can be an integer, it can be a natural number, but it also can be any number written as a fraction or a ratio. So I have any number that can be written as a fraction or a ratio. So that tells me I can do, if I want, -3/4, right? -3/4 is a fraction. If I wanted to convert that to a decimal, that would be -0.75. That decimal can be a fraction, which tells me that even the decimal form is considered a rational number. Next, we have, let's say, 0.3 repeating. That's a decimal. It doesn't terminate like 0.75 did, but it does repeat, which means if I want to convert it, I can say that's equal to a fraction of 1/3. So 1/3 is a ratio or a fraction. Therefore, 0.3 repeating is also rational. So remember, when we're talking about rational numbers, we're not all just talking about whole numbers, 0, any negative integer. We're also talking about decimals or fractions. Any fraction works, or any decimal that terminates, like this one, or repeats, like 0.3 repeating. All right. The last example is an irrational number. This basically means it's any number that cannot be written as a ratio. All right. So if I look at this, let's say the square root of 17. If I take the square root of 17, I know that's going to be 4 point, and then a bunch of numbers after it. square root of 17. Let's see what that is in the calculator. That is 4.1231056. So if we notice, this has no pattern. And it also goes on forever in my calculator. It stops in my calculator, but it goes all the way to the end of the calculator. So that tells me it's going to keep going. And since it has no pattern and it goes on forever, it's irrational. All right. So if we look at this, we already know that for natural numbers, 1, 2, and 3 and on are considered natural. If you look at the second part, a whole number, we know that that is any number that is considered natural. It is also in 0. If I look at this, I have 4 over 2. That's directly underneath this whole number. I know 4 divided by 2 is equal to 2. So therefore, it's also whole. 6 is also a whole number, and the square root of 25 is 5, so it's also whole. If we move up, we look at the integers in the red color. We know that integers are any whole number and natural, so that's why those two boxes are inside integers. We also know -3 is an integer. -10 divided by 5 is actually simplifies to -2, so that's an integer. And then -4. So remember, when you're given a number, make sure that you can see that it's simplified first. So always simplify, and then I classify what types of numbers it can be, what subgroups. The next thing we see is a rational number. So any fraction, so -2/3, 1/2, 5/8, those are all fractions, so those are automatically rational numbers. We then see we have 0.75. That is written as a decimal that stops. Since it terminates, I can write that as a fraction, which we know is 3/4. Therefore, it is rational. And then down below, we have 0.31 with that little repeating bar. That bar tells me it repeats on and on and on. So since it repeats, it can be converted to a fraction. So it's also rational. Looking over to the right side, my irrational numbers, we see that we have irrational numbers of the square root of 10. If I plug that in my calculator, it goes on forever. No pattern whatsoever. The shortcut, 10 is not a perfect square. Since 10 is not a perfect square, then this is not rational. So therefore, it is irrational. 1.6 is also not perfect. So if I take the square root of 1.6, I get an irrational number. Pi also is irrational, goes on forever with no pattern. And just like the square root of 2/3 and the square root of 123 are not perfect numbers, so therefore they're irrational. This last one, this decimal of 0.10100100004, there is no pattern, nothing's repeating, therefore it is irrational. All right, as we look at this problem, it's asking us what is the graph of the numbers -5/2, square root of 2, and 2.6 repeating. So we look at this, we see a number line here. I personally like to always convert my numbers to decimals. So when I convert -5 over 2 to a decimal, I have -2.5. When I have the square root of 2, that's going to be roughly 1.4. And when I have 2.6 repeating, it's already decimal, so I don't need to convert it. So we're going to first put everything in decimal form. Now, looking at this, we have numbers that are all less than between -3 and 3. So I'm going to start with 0, and I'm going to go to 1, 2, and 3. And then we're going to do -1, -2, and -3. The next step is we're going to drag and draw a circle where these numbers belong. So -5 over 2 is -2.5. If I look at my number line, oh, -2.5 is between -2 and -3. So I'm going to draw a circle between them right here. And I'm going to do, oh, that's -5/2. And I'm going to put the original number, not our modified one. Then I look at 1.4. I know 1.4 is between 1 and 2, and it's about in the middle almost. So I'm going to put a dot around the middle, and I'm going to do the original number, which is the square root of 2. Okay? And the last one is 2.6. That's bigger than 2, but smaller than 3, a little bit closer to 3. And I'm going to do the original problem, which is 2.6, repeating. All right, if you look at this problem, it is asking you to circle all of the classifications that apply to each real number. It's either natural, whole, integer, rational, and then it can be repeating, terminating, and or rational. So if we look at the first one, we see that we have 2/3. Since it's a fraction, we can automatically cancel out natural because natural is just 1, 2, 3, 4, and so on. We can cross out whole because that's 0, 1, 2, 3, 4. An integer is 0, 1, 2, 3, 4, and then the negatives. Since rational said it can be written as a fraction or a ratio, since 2/3 is a fraction, then I can assume it's rational. All right? And since 2/3, if I wanted to convert it to a decimal, that would be 0.6 repeating, then I would know it's also repeating. Okay? Since it's rational, it cannot be irrational. So that's all I can circle, and that's it. For -10, I know it cannot be a natural number because that's not a counting number. It can't be whole, but it can be an integer because an integer states that it can be any negative number of -1, -2, -3, -4, and so forth. Since it's an integer, I can write -10 as a fraction if I put it over 1. So since I can write it as a fraction, it's also a rational number. Okay? So if you choose any of the first 3 options, they're automatically going to be everything behind it. It's not a terminating number or a repeating number because we're not talking about decimals, and it's not an irrational number, but it is an integer and it is rational. Now for the last one, we have square root of 81. I always said that you should always check the calculator to see if it simplifies. If we take the square root of 81, I know that it can be simplified to 9. And we know 9 is a counting number. I can count 9 fingers, so that's natural. It's also whole because it's 0 to positive infinity. It's also a number that we can do on the number line, so it's an integer. We usually use integers to label our number line. And it's also finally rational. Okay, so since it's natural, then that makes it whole. Since it's whole, it makes it an integer. Since it's an integer, it makes it rational. Since it's rational, it cannot be irrational. All right, that is it.